let's start. How was quiz two? Was it easy or hard? Moderate? Someone? Okay. All right. So how many of you have watched Week 10? No? All right. So we'll go through the summary of Week 10, and in the next section we will need to do some problems based on that. All right. So first thing is like what did we what are we going to see in week 10? So in week 10, like week 9, we're looking at perceptron. So we'll extend that idea of the perceptron and see certain things. And after that, we will introduce something which is called support vector machine. And then we'll go to soft margin support vector machine and so on. So we'll start from here. I will start from perceptron. So can anyone tell me what the number from perceptron? Okay. Uh, where can you perform perceptron? What kind of data set?
Ma'am, when data set is separable with gamma margin.
Yeah, it is linearly separable. There we were performing, right? So when we were proving the convergence of the perceptron algorithm, what we had also seen that the number of mistakes that this perceptron, this algorithm will make will be upper bounded. So number of mistakes that perceptron will make. So this was one bounded over by r squared by gamma squared. Right? And what was r squared? So r squared was the like the radius, the ball of radius r, where all of my data sets are, right? That was my r. So we had what can we write? We can write r squared. Okay. So my r square was the set of all points, so as all where all the data points was in this radius r, right? All the data points should be in this ball of radius r. And what we were saying is that my data set is linearly separable with margin gamma, right? So the assumption that we had also made is if there is some W star such that uh, this W star transpose xi yi is greater than equal to gamma for every I and for gamma greater than 0, right? We had seen this, we had made this assumption while proving the convergence of this when we're talking about the perceptron. So we had this assumption. So what does it mean geometrically? So there what we had seen is like if we have the data set which are of this kind, like all the say all the positives on one side and negatives on other side. I mean, there is some W star which separates my data set, uh, all the positives on one side and negative on the other side. Then this margin was gamma, right? And this line, you were saying that this line is, I mean, all the points, this line will be the set of all the points such that my W star transpose Xi should be equal to gamma, right? And this line is the set of all Xi such that my W star transpose Xi is equal to minus gamma, right? This is what we had seen. Right? So this is all what we have seen. Now the question is like, how do we check like how good my W star is? Whatever solution you got from the perceptron algorithm, how do you check its quality? How do you check like how good this W star is? So for that, uh, again we will draw same kind of so now what we are going to do is let's say if we had some W star that linearly separates our data set with the gamma margin, then we know that it would look something like this. And all the so if there was a W star that linearly separates my data set with margin gamma, then right, this was my gamma margin. This was my hyperplane, right? So, and I know that this line would be such that our W star transpose Xi is equal to minus gamma, and this line would be set of all Xi for which W star transpose Xi is equal to minus gamma, right? And this is plus gamma. Now, this is one W star, but is this the only W star? Is the question, right? So this is not the only W star. If we look this data set carefully, we can see that we can also find some another W such that which also separates my data set linearly. So if we see this, let's say if we take this W in this direction, let's call it W2 star. So if we take this W2 star, then what we are saying is, then in that case, this will be my plane that separates my data set. So anything on this side would be classified as +1, anything on this side would be classified as -1. And the gamma margin would be this. Right? So this would be my gamma margin. So now here what we got is like for this data set, we could see that there are two W's that we could find, which separated my data set linearly with some gamma 1 margin and some gamma 2 margin, where the gamma 1, like the margin for the W star is this. I mean, this is the margin that my W star is giving, this blue shaded region. And for the W2 star, we got slightly smaller like margin. Right? This is the margin that we got. This pink shaded region. Now, If we had to choose from these two W's, then which W should we go for? Any guesses? Like which W should you choose?
Ma'am, W star.
W star. Why is that?
Because gamma is more, it will give less number of mistakes.
Yeah. So if you have like if we had two such W star and two such W's, but with different gamma margin, then we should then that W would be more preferable. That is a higher margin, because in that case the mistakes that we make, it will be lesser. So here we can say that W star would be preferable. So we'll say that my W star would be preferable.
Man, the blue one you are saying, the
Blue
blue
one,
will be
blue one,
preferable. Yeah, okay.
blue one is preferable. Yeah, because it has more margin, so it has less chances of making a mistake, right? So
Yes.
here we'll say W star would be preferable. Now, okay. Now the question is, will my perceptron algorithm will give such W star that has the highest margin? Need not be, right? So it may not be true that like if you solve some perceptron problem and the W star that you get, I mean W that you get at the end need not be the W that has the largest margin. So if you look at this example, this general example, so we cannot say that my perceptron would always give W star. It could also have given W2 star. Right. So it's just that what it's just that the perceptron will this algorithm will, the number of mistakes that it makes is what we had seen is this R square by gamma square. And when we had derived this result, we had seen that this when we derived this, we saw this was with respect to the W star with the largest margin. Okay, so it just that the number of mistake that will make will be at most this. It doesn't mean that the W star that you get is going to be something which with the largest margin. All right. So now the question is, can we find such W star that has, can we find such W star that has the larger margin, right? Because so far we don't know, like if we could, I mean, my perceptron algorithm is not giving us a W star with that is larger margin. So the question is, can we find it in some way? Can we find such W star which guarantees that I have the larger margin? So what we will see now, like we will try to formulate this problem into some optimization. So now our goal is, that you want to maximize the gamma, right? You want to maximize this margin such that, and you want to maximize over the W and the gamma, all right? And you want to maximize this margin with respect to what constant? So the constant, any guesses for the constant here? Like we want to maximize our margin, but what is the constant here?
Ma'am, W transpose Xi into Ya should be greater than equals gamma.
Huh. So W transpose Xi Yi should be greater than equal to gamma for all I. So this is a problem that we want to solve now. So like if we look at this problem, like if we this is, I mean, basically this is what we are trying to solve. We want to solve this problem, like we want maximum margin. Now here what we are here we are allowing every W, like we can take any W that linearly separate my data set with the gamma margin. So what will happen is, like, if we solve this, like, the problem in this formulation is that, like, if we, let's say, solve, let's look at this figure itself. So if, let's say, this is my set of all xi's for which w star transpose, or let's say, or, okay, w star transpose xi is equal to some value. Let's say it was 5. So w star transpose xi is equal to 5. So if we scale this by a factor of 2, okay, we scale this line by a factor of 2, what do we get? We'll get, again, it will be the set of all xi's such that 2 times w star transpose xi is equal to 2 times 5, which is 10, right? But they are both the same line. So now, again, this 2 times w star transpose, what we can write it as is some another w, let's say w hat, or w dash. So w dash transpose xi is equal to some gamma, right? So what is happening here is, like, we wanted to maximize this. We want to maximize this gamma. We want to maximize this margin. But what will happen is, if we scale my w, like here we are scaling my w star to w star. So when we scale my w, then what happened is, even the gamma got scaled up, right? So if you like change w, your gamma also is changing. So if so happens, like, if you let's say multiply it by w star by 10, then it will become some 50. So your gamma can go to infinity, right? Gamma can go to infinity, which is not what we want. So this problem can be rectified. Like, if you think of this formulation as you want to maximize over gamma with respect to the constraint, such that my w transpose xi yi is greater than equal to gamma for all I, but we will add an extra constraint over here, that is my norm of w should be equal to 1. Okay, so we'll restrict. So in our previous case, where we were not restricting my w, we were allowing any w possible. But if we restrict our w, then in that case, if we take w star to be, let's say, 1, the length of this w star is equal to 1, then even if we scale it down, it cannot be equal. Those lines cannot be equal. So this would work. This should work. Like, if we fix my length of w to be equal to 1, right? So this is the new formulation that we got. Okay. So now what else can we say from here? Here, like, what we saw is that now we want to maximize gamma with respect to these constants. We are restricting w to 1. So when we are restricting w to 1, then what can we see is, like, then we can go back to this figure and let's say this is, let's say, still it is w star transpose xi to be 5. Now, if, let's say, we have, or let's say this pink one is the set of all xi such that w2 star transpose xi is equal to 2, right? The margin was 2. So for the first equation, w star transpose xi to be 5, you can always bring down your gamma to be 1. Now here we are saying that this gamma is 5, but it is always possible that I can, so if I, let's say, divide it by 5, then what will I get? I will get some another W, that would be W star transpose by 5. So let's write this as maybe W star 1, all right? Or not W star, let's say W star dash xi to be 1. So we can restrict my, instead of like saying restrict my W, the length of W to be 1, we can restrict my gamma to be 1. So even if we look at this equation, so what we can do here is we can again say set of all x such that my W2 star dash transpose xi divide is equal to 1. So like if we fix my W, like if we like in case we had fixed our, yes, Ravi.
What variability does gamma represent here?
Gamma is the margin, right?
Okay,
This margin is gamma, right?
okay, okay, fine.
So okay, so um, anyone here? Okay. So what we were saying is like in we came from this formulation. We wanted to maximize gamma with respect to this constant, to adding one extra constraint where my length of W is equal to 1, right? So when we restrict my length of W to be 1, so if we restrict it, this is the, let's say this is the margin, and this is the plane. This is a separating hyperplane. So, and these were the margin. So if we restrict our length of W to be 1, then in that case, what will also happen that my the margin would also be fixed, right? Once we know the length of W, my margin also fixes. So what we can instead try and do is like instead of fixing the length of W to be 1, we can now fix the length of margin. So instead of saying that restrict length of W to be 1, we can restrict the margin to be 1. So what like what we have done over here. So we will now allow any any W star, but we will say that the margin is 1. So we'll allow any such W. We'll not just restrict it to the W with length 1. All right.
But ma'am, you said like when we keep margin more, there is less chance of getting errors. So how will we deal that?
If we okay. All right. No, there what I had said is like if you have two such Ws with two different margins, then I know that we'll prefer that W that is a higher margin. That's true. But now the problem we are trying to solve is like my perceptron algorithm will not give me a W that is the largest margin. Okay. So that is why now we are formulating now we are trying to see that is there any way that we can find such W star that will give me the largest margin. So now we are trying to solve that problem. Okay. So trying to solve that problem, we had come up with this. We had come up with this first formulation of the optimization problem. This one, right? We wanted to maximize this margin. So this maximizing this gamma, we said this can be equivalently written as this, right? But when we fix this length of W, it is almost equivalent to fixing my gamma. So we fixed, so instead of fixing my W, the length of W to be 1, now we are fixing, we are trying to fix the length of gamma to be 1. And we will see how this problem, this is my problem. Again, this is my problem. But we will see that how this optimization problems turns out to be. Because this is not very easy to solve, right? We want to solve this problem, but how can we frame it in such a way that we can come up with a solution? So we are trying to see that. So, so what we have reached till here now is like we will not put any restriction on W. We will allow any W that linearly separates my data set, but it separates my data set with margin 1. And our goal is what? Our goal is to find such W star. Okay. So, all right. Okay. So next, what we are going to see is that maximizing this gamma would be, in a way, it will be equivalent to maximizing the width of the, and what is this width? So we want to maximize this gamma, right? So what we are going to say is that this problem now has become equivalent to maximizing this thing. Just a minute. Just hold on, my pen is not working. All right. So if this is my, let's say this is my W, if this is any W that is separating my data set linearly, and just give me a minute, maybe I will rejoin. Okay, I will rejoin.
Ma'am, you're on mute.
Oh, sorry. Um, Okay, so what I was saying is that if you have some W, which linearly separates my data set with margin one, then this is something, let's say we want, right? So we are allowing any W. So instead of saying that we want to maximize my gamma, now we restrict my gamma to be one, and we want to maximize this width. Okay? So we want to maximize this width now. Now, um, and with respect to what constant, so this with over W such that my W's transpose Xi Yi. So now since we are restricting my gamma to be 1, this is going to be, so Yi is greater than equal to 1 for all I, right? So this is what we are trying to maximize. Now, how can we mathematically formalize this bit? So what can we say is, like, let's say, let's take some point X on this line. So what is my this line? First of all, this line is set of all X such that my W transpose X is equal to 1. And what is this line? This line is the set of all X such that W transpose X is equal to -1, right? So let's say if I take some X on this line where W transpose X is equal to -1, then what will be the width of this width between these two margins, right? So that will be some that will be, let's say, some Z on this line, right? Such that, I mean, will take some X which is such that W transpose X is equal to -1, and we want to minimize. So if there's a point X over here and there's a point Z on this line where W transpose X is equal to 1, then what we are saying is, if we take a line, if we take a point on this line, then in a way my width is becoming what? My width is the distance between these 2 points. And how can you write this distance between these 2 points? That can be written as X minus Z norm squared, where you're minimizing over W, such that, and what do we want? We want such Z such that my W transpose Z is equal to 1, because we want that Z to be on the other line, right? So such that my W my W transpose Z becomes 1. So now this is my problem. So if we solve this optimization problem, what we get is that I mean, the width of the W, I mean, this norm of X minus Z square for some optimal W is for some W. So this width turns out to be, after solving this optimization problem, is norm of not norm of 2 divided by norm of W square. 2 divided by norm of W square. So well, this was for this minimizing this distance. This one. Okay. So instead of minimizing X minus Z norm square, we minimized 1/2 norm of X minus Z square, and we got this width to be 2 upon norm of W square. Okay. So now this optimization, my original optimization problem, now that can be formulated as minimization of, sorry, this was max, right? We wanted to maximize this width. So what did we get? We got max of W 2 upon norm W square such that my W transpose xi yi is greater than equal to 1 for every I. Now we know that this maximization problem can be also written as, so this is equivalently, this can be equivalently written as, so max of this can be written as min over norm of W square by 2. This we can write such that W transpose xi yi is greater than equal to 1 for every I.
Ma'am,
Hmm.
ma'am, in the width, why we are dividing it by like 2 is the distance between the two, and why we are dividing it by norm squared?
No, this we got after solving this optimization problem. This is not something I wrote directly looking at this. So you have to solve this optimization problem and then only you will get this this term.
Okay.
So basically this width that we're writing over here will turn out to be 2 upon norm square after solving this optimization problem.
Okay,
Okay.
fine, ma'am. Okay.
And mhm. So now we will try to solve this problem, that is min over W, norm of W square by 2, such that W transpose xi by a is greater than equal to 1. So again, what we wanted to do is, like, if we have a set of data point, we wanted to find a W star which gives you the larger margin. Right? This is my original problem that we started with. We want a W star that gives me the larger margin. So the optimization problem that we have right now is min over W, where norm of W square by 2 subject to this constraint. So this is like, before going for this, before solving this, what we will also see, I mean, I think you have also seen this in your MLF class. So what we will also see is how can we solve the primal and the dual problem. Okay, so that we will look at. So, okay, so we'll just look at the primal and the dual first, and then we'll come back to this equation, like how to solve this. So let's say my problem is, the primal problem is min over some f of W, right? Subject to the constant g of W less than equal to 0. Okay. So to solve any constraint optimization problem, we know we can use the Lagrangian method. So what do we do in Lagrangian method? We define a Lagrangian function, and it will be a function of W and some lambda, right? And this would be what? This Lagrangian function would be equal to f of W plus some lambda of g of W. Let's set it to alpha itself. So some alpha, which is a constant. So alpha of g of W, right? Where alpha is a real number. So what we can do is, like, now, okay, so this is my this is my Lagrangian, right? So now let's consider, like, if we, let's say we want to solve for max of this L of W alpha over alpha greater than equal to 0, where we fix some alpha. in, sorry, we fix some W. We're fixing some W, and then we try to solve for this max over max of L of W comma alpha greater than equal to 0. So this will be equivalent to solving my max of L of W alpha is going to be what? F of W plus alpha of G of W, right? Where alpha is greater than equal to 0 is what we are restricting to. We want alpha which are greater than equal to 0. Now, see. So we want to maximize this term. So in order to maximize this term, like if we change certain conditions, this will give me some different values. So like if we say that my G of W, so if we say my G of W is positive, that is greater than 0, then what will happen? So if this is positive, I mean, if this is greater than 0, and my alpha is something which can take any R positive value, like any alpha it can take, right? And my G of W is also positive. I mean, it's also plus sign. So if we take if we want to maximize this F of W plus alpha G of W, it can take the value up till infinity, right? So in that case, if my G of W is greater than 0, the max of, I mean, this will turn out to be infinity. Maximizing, I mean, its maximum value can go till infinity, right? But if we restrict my G of W to be less than equal to 0, right? Then in that case, what will happen is, like, let's say I take some negative value for G of W. So if I take some G of W to be negative, and I know my alpha is positive, then alpha of G of W is also going to be negative, right? And if we add some negative value to my F of W, then that value is also like going to be lesser, right? But I mean, we don't know what this FW is currently, but assuming that my G of W is negative and my alpha is positive, my alpha G of W is always going to be negative. So you're subtracting something from FW, and that term will always be lesser as compared to then this term itself goes to 0, because my alpha cannot take negative value, and we have assumed that my G of W is negative. So I cannot take my alpha to be lesser than 0. What I can do is, if I take, instead of G of W to be less than 0, if we take G of W to be equal to 0, then in that case, the maximum value that you get is F of W, right? So for this condition, the maximum value that we get is F of W. So what we are saying is, like, let's say we had some space over here, and this is the set of, we are saying is that this will contain the set of all W's such that my G of W is less than equal to 0. Okay. So any W that belongs in this region, the maximum value that it will take is F of W. So it can be anything. I mean, if it can be like, if I take this W, then the maximum of this will also be FW. If I take this W, the maximum of this will also going to be FW, and so on. Any W I take, the maximum value is going to be F of W. But if I take any W outside this region, right? Any W that I take outside this region, this is always going to evaluate to infinity. Any W that I take outside this region. So, I mean, what my original problem was. So my original problem was that uh, uh, we wanted to minimize this F of W subject to this constant, right? And what we saw is that we want to, like, if we did this, like, if we maximize this L of W, so if we maximize this F of, or f of w plus alpha of g of w, where alpha is greater than equal to 0, then this solving this problem was in a way equivalent to solving my um, f of w, right? Yeah. So okay, so right. So for this particular constraint, where g of w is less than equal to 0, so this was equivalent to, so this turned out to be f of w, right? This max of f of w plus alpha g of w over alpha greater than equal to 0. This is what we have. Now, if we if we minimize this, max of over alpha greater than equal to 0, minimize over w, and this f of w plus alpha of g of w. So now if we want to minimize this w, minimize this f of w over w, so this becomes equivalent to min of f of w, right? Min of f of w over w, such that my g of w was less than equal to 0. Right? And this was my original problem that we started with. We started with min of f of w such that this happens. And what we found out that this problem can also be written as min max form, where we're writing min of f of w, I mean original problem as min over w max of f of w plus alpha g of w over alpha greater than equal to 0. Okay. So from the convex, so from here, what further we can say is, from the convex duality, I mean, if my function f and function g are both convex, then this can also be equivalently written as max over alpha greater than equal to 0, min of f of w plus alpha of g of w. Right? And this is min over w. So now, where my original problem was this, we saw that this can also be formulated as this, and this using the convex duality, where my function f and g are both convex, we can write min max as max min. So this can also be written as this. Okay. So instead of solving this problem, now I will solve this problem. All right. So what can we say? What we can also say is like this was just one constraint. Now let's say if we had more than one constraint, how can we write it as? So let's say my problem was min over f of w over w, such that my gi of w is less than equal to 0 for all I, and let's say my I is varying from 1 to so on till n. All right. So if we have to write the Lagrangian function, then how can you write this problem as? This problem can be written as min over w max over alpha greater than equal to 0. So I mean, if you have I constant, where I varying from 1 to n, again you have alphas will be n. So alpha will be of something like alpha 1, alpha 2 to alpha n. And what we will say is that my alpha 1 is greater than 0, alpha 2 is greater than 0, so until alpha n is also greater than equal to 0. So this is what we mean by alpha greater than 0 over here. So max of alpha greater than 0, and this is f of w plus alpha 1 of g1 of w, so on till alpha n of Gn of W. Alright, this is what we have. So I mean, in case I mean, if f and all the GIs are convex, then again this min max can be written as max min. So you can write this as max over alpha I greater than equal to 0, min over W, and f of W plus alpha 1 G1 of W, so 1 till alpha n Gn of W. Okay, so this is my problem now. So if we now go back to my original problem of the perceptron, where we were trying to find a W star with the highest margin, with the largest margin. So where is this problem? This is the problem that we wanted to solve, right? So this problem we go back. Now my problem was min over norm of W square by 2, subject to the constraint W transpose Xi Yi is greater than equal to 1 for every I. Right? Now, I know that um, this is linear, right? So this will also be convex, and I know this is quadratic, so this is also going to be convex. So here, and from this primal and dual problem, what we saw is that any min of I mean this problem could also be written as max of, no, not max of, min of, right? Yeah. So min of W, max of alpha I is greater than equal to 0, and f of, so here what is f of W? My f of W is norm of W square divided by 2 plus alpha 1. So now see, when we were trying to formulate the dual problem, my G of W was less than equal to 0. So how can this constraint can be converted to be of the form G of W less than equal to 0? So you can write this as W transpose Xi Yi minus 1 greater than equal to 0, which can also be written as 1 minus W transpose Xi Yi to be less than 0 equal to 0 for FPI. So now this is my G of W, right? So what can you write? So now this would be sum over all the alpha. So alpha I, where I is varying from 1 to n, and G of W. And G of W is my 1 minus W transpose Xi Ya, right? This is my problem. So using the min-max, duality of, convex duality, we can write min-max as max-min. So this can be written as now max over alpha I greater than equal to 0, min over W, half of norm of W square, plus sum over alpha I, 1 minus W transpose Xi Yi. Okay. I is varying from 1 to n. Alright. So this is my problem now. So what is so what is happening here is like suppose like when we fix my W, then like here, this was my L of W, right? This is my L of W alpha. Okay. So when we okay. um, All right, we'll see this. So what we saw so far is like um, we started with this, like we have to solve this problem, this problem, and the dual of that we are able to find it as this problem. This is what we have done so far. Hmm.
Initially, we have considered norm of W is equal to 0.
Norm of W square.
Norm of W is equal to 1.
Ah,
And from there to how we terminated to gamma is equal to 1. Gamma greater than is equal to 1.
no, okay. So we started with we started with we didn't start with that. So like when we were trying to maximize my gamma, then there what we observed is we should put some restriction on W also, because when we were scaling it, at the moment I scale my W, what was happening is that my gamma was also getting scaled up. And if we do the max of that gamma, we'll get like it can go till infinity. So that was not ideal. So what we said is that okay, let's try fixing my let's try to stick to this, that my norm of W is equal to 1. So from there, like if we the moment I fix my W, my gamma is also fixed. I cannot change my gamma also there, right? So in a sense, my gamma was, depending on what my F is, my gamma will also change accordingly. So what instead of instead of fixing my W there, what we said is let's try and fix my gamma instead of W. Okay. So like if we take any hyperplane, any line, right? Like let's say when we took some W transpose X is equal to 5. So given any line, we were able to scale my W and bring my gamma to margin 1, gamma margin to be 1. So uh, instead of like fixing my like where we were saying that we will fix my W, what then we ended up doing is like now we can allow any W that linearly separates my data set, but uh, it separates my data set with gamma margin. We'll take such Ws. So from there, like this constraint that you're seeing over here, that W transpose Xi by A greater than equal to 1. So that's how this gamma has become 1 here. And what we saw that when we took this gamma to be 1, and now what we want is we wanted to maximize the width between the space between the space that you get, the margin that you get, right? So we call it as width, and we wanted to maximize that instead of maximizing my gamma, we wanted to maximize my width. And that width that turned out to be 2 upon norm of W square, right? And since we wanted to maximize this, that was equivalent to minimizing this norm of W square by 2. So that's how the problem has like changed a little here. And now using this primal dual thing, we're able to write this in now max of alpha is min over my Lagrangian function. So this is where we are now. Okay. So now we will try to solve this problem. Okay, instead of solving this, we will solve this. So now what we have, I'll just write it again. So now my problem is max over alpha I greater than equal to 0 when over w half of norm of w square plus sum over alpha I, where I is going from 1 to n, 1 minus w transpose xi yi, right? This is my problem now. Okay. So now you want to maximize this term. So if you fix alpha, some alpha greater than equal to 0, then what will happen? You want to solve this problem. So, and this problem is, I mean, this term here is what? This term was my, so half of norm of w square plus this term, right? So if we take the derivative of this, what do you get? So if you take the derivative of this, like if you take 2L of W alpha by dou W, right? Because we want to minimize this with respect to W. So if you take the derivative with respect to W, then in that case, you get, what you get is some W, like this derivative is just W, plus what will you get here? So this will be alpha I yi, which will be just 0. Then what you will be left with is minus of alpha I xi yi, right? So W plus sum over alpha I minus of xi yi, right? This is what we get. I varying from 1 to n. So for this, so for any alpha that we fix, we are going to get this. So let's call, like for this alpha, like for this specific alpha, let's say we got, we solve this, we get some W alpha, let's say this is W alpha, let's write W alpha. So now they're taking derivative, now equal to 0. Then what do you get? What we get here is my W alpha turns out to be sum over alpha I xi yi, where I is varying from 1 to n. Right? So if you take like if you take any, like if you fix any alpha which is positive, what we got is that my this optimal W, that is W alpha here, is nothing but the linear combination of my data points xi and yi. This is what we got. And if we can write it in the form of matrix, this can also be written as, yeah.
What is this W alpha?
W alpha is like it's nothing. I mean, it's just W. So we were trying to see if you look at this, I mean, minimization problem. To solve this, you will take the derivative of Lagrangian, right? So this is my Lagrangian, right? And the derivative of this Lagrangian is nothing but W plus alpha I minus xi yi summation. But why I have just written alpha over here is because we are fixing one alpha, right? We are fixing some alpha. So just to denote that for this alpha, we have just written in the subscript, nothing else.
Okay, okay.
Just to denote that Given any alpha, you get the optimal double to be linear combination of your data points. So if you like try to write it in the form of matrix, so this term can also be written as your matrix y x times y times alpha. So this is my W. Where what is my x? What is my matrix x? So my matrix x here, matrix x is, you have x1, so on till xn. Matrix y is y1, y2, so on till yn. This is 0, this is 0. And your alpha is alpha 1, alpha 2 to alpha n. Okay. So this W can be written as xy, this matrix x times y times alpha. So now, okay, so we got, when we solve this, like when we took the derivative, put it to 0, this is the W that I got, right? So now what is this value here? I mean, what will this turn out to be? This thing is a question, right? For this W. So for this W, which is xy alpha, now this problem, which is min over, you have to find min of W, L of W comma alpha, right? So the W that you got is this. So the minimizer, basically to find the to find the value of this, the whole thing. Now we'll have to substitute the value of W in this LW alpha, right? So what do we get after this? We'll get 1 upon 2. So norm of W square is going to be norm of xy alpha. We'll just write this. And some over W, I mean, you just replace W with xy alpha. And when we solve this problem, what we will get is when you when you substitute this W to be xy alpha over here, then you will this was max over alpha greater than equal to 0. So this inside term is just going to be alpha transpose this vector 1 minus 1 upon 2 xy alpha transpose xy alpha. This is what we will get once we substitute this W to be xy alpha in this equation. So now this is my problem. So where we had started with, and we had, my primal problem was, so my primal problem was min over half of norm of W square subject to the constant that W transpose xi yi is greater than equal to 1. And my dual problem is max over alpha greater than equal to 0 of alpha transpose vector 1 minus 1 upon 2. This is xy alpha transpose xy alpha. So it can also be written as alpha transpose y transpose x transpose x y alpha. Right. So this is my dual problem. So now, when we converted this primal problem to the dual problem, so here you have like, you can see you have this X transpose X right here, and this is nothing but your kernel, right? So uh, this is, I mean, your X transpose X could be what? My matrix X is this D cross N matrix, right? So N cross D. So this X transpose X is going to be in N cross N, right? And my primal problem was in like D cross D. So in case where your number of features is quite large, like only in the case where the number of features that or your D is very large, this dual solving this dual problem is better. I mean, it's easier to solve this dual problem. But this is only when the case your number of features is quite large, but that is also not always possible. So that is one thing. I mean,
What is the number of feature?
like number of features if it is quite large, like if D is very large.
Okay.
So in that case, because your dual problem now has X transpose X, right? And that is a your N cross N matrix. But if you look at the primal problem, it is it will be in, it has dimension D, right? Xi has dimension D. So solving the dual problem is going to be easier when you have D to be very large. So in one way, this is going to be useful. Then the second thing is that in my dual problem, the constraints are easier. That is like in dual problem, now your constraint is that my alpha I should be greater than equal to 0. That's all. But when I look at my primal problem, my constraint is that my W transpose Xi Y is greater than equal to 1. That is a little difficult, right, to solve for. So in this way also it is helping us. And the third and the very important thing which we are gaining from solving this dual problem is that now in dual problem, if you look at this objective, you can see this X transpose X, which is nothing but your kernel K, right? So from here, you can also see that uh, this can also be like, this problem can also be kernelized, right? So if you have if you're not just talking about the linear separability, if you have like quadratic uh, structure and so on, in that case also you are able to classify easily using this technique. So that is one way where it can also help. And the next thing that we also saw is that the optimal W that we found, I mean, that was this alpha I xi yi. So this is nothing but your linear combination of the data point. So that is also one thing that we gained from here. So using this W, which is sum of alpha xi yi, what we can say, what we can get from here is like we will be able to know like which data point are contributing uh, towards your finding that optimal W, right? So and how do you check that? I mean, in case your alphas are 0, so I mean from there we can say that those data points are not contributing in finding my Ws, right? But if my alpha i's are greater than 0, then from there we can from there we can say that, I mean, we will be able to find those data points which are contributing towards finding my optimal W star. All right, so this is what we are gaining from here. So from here, we will introduce something which we also call it as support vector machine, support vector machine. So now, um, like we stopped here, right? We want. I mean, all we said is that my optimal W is the linear combination of data point. But now we have to find what are those points which are important points. So to find that, how can we how can we proceed with that question? So now what you can see here is, let's say, so I know that my primal problem, this is nothing but of the form min of f of w subject to the constraint g of w less than 0. And we were able to write this problem as min over w max over alpha Lagrangian, which is f of w plus alpha g of w. Right? This is what we were able to write this as. And what I saw is that using the convex duality, this is equal to max min. So if you write it in f of w and g of w, it will turn out to be max over alpha greater than equal to 0, min over w, f of w plus alpha times g of w. This is what we saw. All right. So this is my primal problem. This is my dual problem. Now, if we say that, suppose since this is a primal problem and we are minimizing over w, so let's say w star is my primal solution. And here, this is my dual problem, and we are maximizing over alpha. Let's say my alpha star is the dual solution. Okay. And since both these problems are equivalent, both these two optimization problems are equivalent, then what we can say from here is, if W star is the final problem, then it means that uh, this whole thing, can be written as max over, because you obtain some W star that is minimizing this, right? So you can write this as max over alpha f of W star plus alpha of g of W star. Okay. And since alpha star is the dual solution, then what you can write as, this can be written as, this will be equal to, when alpha star is the dual solution, then this will become min over w f of w plus alpha star g of w. Okay. And we are saying both are equal because both the solutions should be equal because those two problems are equivalent. So now, this is my primal solution and this is my dual solution. Uh, so when we are looking at the primal solution, what the constraint that we had was g of w star is less than equal to 0, right? We had this constraint that g of w star has to be less than equal to 0. And from there, what we had found that this maximization, I mean, max of f of w star plus alpha of g of w star, this was coming out to be just f of w star, right? This we had seen. Because anything like, if we were assuming g of w star to be greater than 0, then in that case, this was going to be infinity. So that is not what we wanted. So when we took g of w star to be less than equal to 0, we got the max of this to be just f of w star. So from here, what we can say is, we can write max of max of f of w star plus alpha of g of w star over alpha is equal to f of w star. Now this solution, this value is going to be equal to min of w f of w plus alpha star g of w. Okay. Yeah. So this is these two are equivalent. So this f of w star is the, now what we're saying is that this is minimum of f of w plus alpha star g of w, right? So in general, if we take any w, this should be greater than equal to, so any w we can take, right? So why not, let's take w star. So this should be greater than less than equal to f of w star plus alpha star g of w star, right? This can also happen. So from here, what we got is that my f of w star is less than equal to f of w star plus alpha star g of w star. So this will get cancelled out, and what do we get is that my alpha star g of w star is greater than equal to 0. This is what we got. But we also know that my alpha star is greater than equal to 0. From my dual problem, this is what we have assumed, that my alpha star is greater than equal to 0. And from the primal condition, we knew that my g of w star should be less than equal to 0 for my optimal w, right? This is, we know. So if you take the product of these two, which is alpha star g of w star, this should be less than equal to 0, right? So we got two. So at one place, so we got alpha star g of w star to be greater than equal to 0. On the other hand, what we also got is alpha star g of w star is less than equal to 0. So this can only hold, like these two conditions can satisfy only if my alpha star g of w star should be equal to 0, right? So this is the only case when this can happen. And this equation is what we call it as complementary slackness condition. So if you had, if you remember from your MLF course, so when you're looking at optimization problem, this was called the complementary slackness condition. So here, like if any of the term, either alpha star or either g of w star, if any of these term is less than 0, other term has to be um, uh, equal to 0, right? So if I say alpha star is less than 0, then g of w star should be equal to 0. Or if g of w star is less than 0, my alpha star has to be equal to 0. So this condition is called the complementary slackness condition. So this was with respect to one constraint. Now, if you have multiple constraints, then this can be written as alpha I star g I of w star is equal to 0. So remember, like we started with the question is, we want to find my w star that gives me the largest margin. Such w star we wanted to find. And what we saw that this w, like after solving this optimization problem, what we saw is that this w star is nothing but the linear combination of my data point, right? Which you call it as alpha I xi yi sum over alpha I xi yi. So from there, what we wanted to see is like this is giving me an idea of like which data point are contributing towards finding my wi. So to find that at which data point are contributing towards my w, we need to know that which alpha i's are positive, because only in the case when your alpha i's were positive, you can say that this particular point is contributing towards my finding the optimal w, right? Because if your alpha i's were 0, those data points would not have been contributing. So now the thing is that we want to know where are those data points lying where my alpha i's are strictly positive, right? Not that we want that alpha I should be greater than equal to 0. What we want is that my alpha I is strictly 0, because that will give me the idea that where are my data points lying on, where are my where are my data points lying which are contributing towards finding my optimal W. So from here, what can we say? Um, from here, you have alpha I star, and what was my GI of W star? It was 1 minus W star transpose xi yi, right? And this is equal to 0 for all I. This is what we can write. Now, since we want to find such xis which are contributing towards my W star, we will have to take alpha I star to be greater than or equal to 0. So we'll now say that, okay, let's say that my I star is greater than 0. Then if alpha I star is positive, if this is positive, and I'm saying that this whole term is equal to 0, then if alpha is positive, then the another term will have to be equal to 0. This is from complementary slackness condition. So from here, we can say that my 1 minus W star transpose xi yi has to be equal to 0, right, for every I. And this can be written as that my W star transpose xi yi is equal to 1. Right? This is for every I. So, um, W star transpose xi yi is equal to 1. This is what we got. So, looking at this, what can we say? So, what we can say is that the points which are there on those margins, only those points are contributing towards my optimal W star, right? Because this is strictly equal to 1. And these are the lines that you have. Let's say this was my W star, and you had all the so, positive points on the other side of this, and all the negatives on this side, right? And this was my separating hyperplane, right? So what we can say from here is that only the x where which are only the points which are there on the margin, which is on this line, I mean these points. So these points are the one that are contributing towards my this W star. So this is what we get from here. This is one operation. And the vectors which are lying on the margins, they are given special names and they are called the support vectors. So any points that you see on the margin, they are called the support vectors. Okay. So they are called support vectors. Any vector that you're seeing on the margin, they are called support vector. And these are the only points that contribute towards finding my W star. So you are able to compress your like data point here, right? From a very large data point, you are able to find you are able to find the points which are actually important. So here the compression is happening. right? And this algorithm that we just saw of finding these points is what we call the support vector machine, and in short, it is also called SVM. So what we can say is that my W star is just linear combination of like some sparse linear combination of my data points. So this was about support vector machine, and um, okay, so like this is fine. Like we are able to do the compression here, and we are able to find the important vectors which are contributing towards finding this optimal W star that gives me the largest margin. But the question is like, what if a data point has outliers? So does this SVM algorithm works for certain those kind of data points? I mean, the data point which has outliers. So what we observed is like in that cases, I mean, in certain cases where you have the outliers, there this SVM will not work, right? So let's say if this was my positive side, right? This is positive side, and let's say if I have some data point which is minus, and on the other side I have some positive data point, then um, I mean, if we look at this figure, I know that this can be separated. I mean, the data point is, I mean, data point can be linearly separable, right? From here, this is what we can see. But because of these outliers, we are not able to find those, we're not able to find which W star will separate this data point. So to tackle this problem, we are going to introduce something which we call as soft margin SVM. So in the cases where your data point has outliers. So now you have a new, I'll generalize this, and this is a soft margin SVM. So in soft margin SVM, like what we are trying to do is that we will not say that any particular any particular W which, so like when we are solving our original problem of linearly separating the data set, uh, then we looked at only such W's which linearly separated my data set, right? But now in soft margin SVM, what to solve this outlier problem, what we are going to assume that take we'll consider every W. So we'll make every W feasible, okay? And then we'll work with that. So if you take any W, like since we are not restricting our W, I mean, we're not saying that we'll take only that W which are linearly separating my data set. Now we are saying we can take any W, right? So if we take any W, then in that case, that W might classify some data point correctly, and it may not classify some data point, right? So if if there are some data points which are not correctly classified, then what can be done is like the points which are incorrectly classified can pay some amount and go to the right side. Like they will have to pay something to go to the right side. Let's say if like this data point is negative, is on the negative side, right? So if I take this W star, then I know this W star is going to classify every point correctly instead of these orange points, right? So what can happen is, since we are allowing any, and I know that this W star is not linearly separating my data set, but in case we allow this W star to be a part of the solution, then what can happen is these orange data point can pay something to go towards the right side. So this can pay something to go on this side, and this can pay something to go on the other side, so that my W star is able to classify hard point. So where my original problem was min of uh, min of half of norm square over W subject to the constraint W transpose xi yi is greater than equal to 1 for every I. Now we can change this. This problem can be modified to this problem can be modified to uh, min over half of norm square, right, over W, subject to the constraint that my W transpose xi yi plus, now we'll take some epsilon also. So epsilon is the amount that my data point will pay in order to go to the right side. So this is some quantity, and we are saying this should be now greater than equal to 1. And this epsilon I will always be positive, right? So this is the data, this is the problem now that we have come up with. So since we are, okay, so in soft margin SVM, like since we allowed any data point to be feasible, then in that case, like if let's say if my W, if I allow, since we are saying that we can allow any W, so if we allow the W to be all zeros, if we allow W to be a zero vector, then in that case, like since epsilon I mean this whole thing has to be greater than 1, then epsilon I can pay an amount of one unit, and it can, and that will also work. I mean, and it can pay 1 and it can go to the right side. But this this term, this my original, my objective will be 0, right? We so that is something that we don't want. I mean, we don't want in that case, like the W will be the W, which is the 0 vector, is going to be the optimal. So that will happen every time. So what we'll also have to look into is uh, anyone cannot just pay, I mean, any data point can not just pay something and go to the right side without it's affecting my objective, right? So we'll do one another addition to my objective, which is some C times some over epsilon I, where I is going from 1 to n. So all the amount that every data point pay to go to the right side, we multiply it by some factor, and which we are calling it as balancing factor. And this is my hyperparameter here. So now this problem um, can be written as this, right? So this was about, I mean, we have just introduced a soft margin in week 10. When we go to week 11, we will look at this part in more detail. So this is just the introduction of what soft margin SVM is and how it can be helpful. So this is where we'll stop. Any question here?
Ma'am,
Mm.
earlier you have written this problem without adding the constant. And after this adding constancy, summation I equal 1 epsilon I, how it is different?
You're saying this, right? This one.
Yes, yes. Earlier you have
Um,
written it without that constant, and after adding constant, how it is making difference?
so see, so when we had not added this constant, then in that case, I mean, we are not penalizing the data point in that case, right? So in case, like, if we take this example only, so if if I am not penalizing my data point, then what will happen is that this data point, since it has to go on the other side, it can pay something and go to the right side. This data point can pay something and go to the right side. In that way, any data point can pay some unit amount and it can go to the right side. So this is not what we want. So what we want is that you cannot just go paying some amount to the right side. So you should be penalized for doing it. So if a point is going, if paying something and going to the right side, so this penalization is happening over here, right? Here. So if and this constancy is what we are calling it as an hyperparameter, and it kind of balances like how much should one be penalized or something, right? So this is going to your C is basically saying like if if a data point, if any data point is going, if paying something and going to the right side, uh, how much does it cost to go to the right side? This is how we can think of it. So what happens if C is 0? If C is 0, that means key. Uh, if C is 0, then in that case, what will happen? In that case, this my objective function remains 1 upon 2 norm of W square, and this is my constraint, right? So in that case, I mean the minimum. I mean, you want to minimize this. So the W that will satisfy this is going to be 0, right? That will be the most ideal in that case. Yeah, do you agree with this? In case C is 0, we are saying C is 0. If C is 0, then my problem is to minimize this, right? Minimize now W square by 2. So, and since in a soft margin SVM, we are allowing any W, we are not putting any restriction on W. We are not saying we'll take only that W which are linearly separating my data set. No, we are taking any, we are allowing every W. So if we are allowing every W, I know the minimum W, the W that will give me the minimum value of norm of W square by 2 is going to be always 0. So this 0 vector is always going to be my solution, no matter what, right? You agree from this statement that 0 would be my solution always? So that is why, to compensate that, what we're saying is any point cannot just go to the right side. They should pay something. They should be penalized to go to the right side in a way. And that is what we are capturing through this second term, which is C times sum over epsilon I. And epsilon I is the amount that every incorrectly classified data point paste, or any data point that pays to go to the right side. So if some certain points are already on the right side, then in that case, epsilon I would be 0. If they're not, that will get added here. And which, if someone, which data point to be taken, which data point pays how much, it's all will be given, like that will uh, that will come under this C. So C is your hyperparameter here. So that is why the second term in this objective is important. Okay. Anything else? All right. So,
Ma'am, please share this PDF, ma'am.
mm, I mean, I have not
Like,
done something new here. I mean, you can, if you look at source notes, it's all the same. So, let's say you can go through
ma'am, but
that
we can
place.
like one because we have gone through this once, so it will be a bit easier to understand when we see.
Okay. All right. So, yeah, I will share this and we'll stop here because um, the soft margin SVM is something which we're going to look into more detail when we go to week 11. There's nothing more to discuss. Um, yeah, anything else apart from this? All right then. We'll close for today and we'll meet on Friday next.
Thank you, ma'am.
Thank you.
Thank you so much, ma'am.
Yeah. Thank